We have Adam Casella, who is CTO and co-founder of SnapRoute, and he is going to be, now my mind just went blank, so I'm going to let him tell you about what he's talking about. So welcome, Adam.
Cool. Hi, everyone. I'm Adam Casella. I was just introduced, and I am a co-founder and CTO at SnapRoute. For those of you who do not know me, my roots come from an operator. So I built, ran, and fought some of the largest networks in the world when I was at Apple. And so what I'm here to talk to you about today is something that's really near and dear to my heart. It is the problems and the gaps in solutions that I saw while running these networks at Apple. And so that ended up driving me to found SnapRoute to try to fill in some of those gaps and try to address the problems I saw for how we were approaching network architecture, particularly on the network operating system side, and what we weren't able to do and what I think we can fill in. So let's start out here. So operating networks is hard. It's getting harder every day. Networks are getting larger, they're becoming more complex, and much more difficult to ensure we have consistency, get the convergence time we need, and the runtime serviceability that's required to make sure that we can resolve day two operations. Applications are becoming more demanding of our networks. They want more throughput, more bandwidth, better latency, and they're becoming more portable. We have a mix of applications that sit both on the cloud, on-prem, and other locations. And we need an infrastructure that becomes more agile and more mobile to go, resilient to go ahead and respond to the changing needs of the application. So now I know we've talked about this in depth for the last 10 years about how to solve networks and what are solutions that are existing out there. And so you'd think that this problem has already been solved. So anyone who's run a network is very clear with this type of image right here, where you have that 3-year temporary cable that's going to be pulled out at any moment that you won't need anymore, but ends up sitting there until that device gets decommissioned. So innovations in our industry have been incremental. We haven't made any fundamental changes for how we go ahead and manage a device. Sure, we get APIs now, but those APIs a lot of times end up being wrapped around a CLI that was already existing. Or we get tools like Ansible and Puppet and Chef, which are really great at automating config, but don't have that good of a concept of how to manage state. And really, at the end of the day, they end up sitting on top of an architecture that was never designed to be automated. So that day two operations is still unsolved. We cannot get from these tools the state of the network by looking at the config. We either have to pull the config that's on there, we have to go ahead and then make some translation to say, hey, this config means I expect this state to happen on the network. It's not something we can intuitively see or declare on that particular OS. And because of items like this, we end up with these very long security cycles. We can't go ahead and manage how to go ahead and patch or fix a particular issue that we see. It takes a very long time to do it. We have to do it in a monolithic way. We have to either do a complete image upgrade, which takes downtime and items we have to deal with from that perspective. And as everyone knows, maintenance windows are becoming smaller and smaller, and it's getting harder to go ahead and schedule those downtimes. We live in a 24-hour-a-day world. People expect to be able to pull out their smartphone anywhere they are, any time of day, and get access to that application. If they don't get access to that application, they try a different app or believe that app isn't good. So the pressure on the network and the app teams to go ahead and deliver a better time to service is huge. This is not a sustainable model long term. Eventually, this all breaks down. And this has been seen by our public cloud and hyperscale guys. They've looked at how to go ahead and approach this, and they've realized that their business has been inhibited to be able to grow at the need they want because they can't get an infrastructure that reacts to what their needs of their application. So they decided to go ahead and roll their own. I mean, Facebook, Amazon, Google, they don't roll their own NOSes, and LinkedIn, with Sonic, it was just said by Zaid, don't roll their own NOSes for fun of it. They don't sit there and go, yay, let's go ahead and manage this software and not have to go ahead and buy it from someone else. So how do we get here? Well, it really started if you go back to how We wanted to go ahead and get connectivity with the internet and really had this obsessive nature to go ahead and ensure we had connectivity to all portions of the world and devices without having to think about the day two side of it, the usability at runtime. We just want to make that device get it deployed, make sure it was out there, and never have to think about it again. And we got this concept that more features meant a better OS. As we went around this journey, we got more items that were placed in there, more functionality we can do, and that drove us to believe that the operating system that we were running was better. And we had this assumption that the applications sitting behind our networks were never going to move. If we deploy an application, it's going to be there in that same location until it gets decommissioned thereafter. So we really had the concept that you put the network in, you never think about it again, it's going to be statically set from the standpoint of a config, and didn't have to respond to a cloud-native application that may be in one location and then move quickly to another. Maybe it's in rack A, and then all of a sudden it needs to be in rack Z because the resources changed. And so multi-year uptime was something that we all looked at with envy. I know me personally, if I saw a device that was running 10-year uptime, I said, wow, that's a really stable device right there. I'm really impressed by that. I wish I can get that type of uptime for my equipment. But in today's world, what I see are security flaws that haven't been fixed, bugs that haven't been resolved, and features I can't get access to. Can you imagine in the compute world, running a device out there for 10 years with no ability to patch or update? We'd be running Ubuntu 8.04 or RHEL 5.2 in production. So what about disaggregation? That's the solution to all our problems, right? We split the hardware into software. We're going to get this new innovative network operating system that we can do all these items with. Well, in reality, the same authors, in many cases, who wrote from the vendor standpoint, that wrote the network operating systems on the traditional OEM devices, wrote the ones for the disaggregated world. So it's the same problems and the same issues we've seen before. It's still a monolithic management method. We have to do a rip and replace upgrade for those devices and to go ahead and move from version A to version B. Sure, we have hotfixes. However, as anyone knows who's running a shop, that you might apply hotfix A, but in order to do an upgrade, you might have to remove that hotfix to do the upgrade because that's what's supported by that vendor. And the security model has not changed. Sure, we've gotten new tools that allow us to manage these things slightly easier, but we still cannot fundamentally patch problems when they arrive. If I have an issue that ends up being in BGP, I need to upgrade all the other associating protocols with it to get that fix. And all the new features I now have to go and retest and recertify to know that I'm not going to see an issue when I deploy it in my network. And I think this is said best from a colleague in this world, and it's basically that disag is the last adoption of the old world with new tools. I mean, this is a perfect example of like this. Who said the parallel port was dead? So we can do better as a networking industry. We can learn from cloud native and the people in the compute world and their approach to how they've go ahead and looked at operations and what they've solved. They haven't solved this with tools. The DevOps world hasn't gone through and says, you know, we're going to throw more tools at this to solve this issue. No, they've solved this by changing the underlying architecture, moving to containerized microservices, declarative state for their applications with automated verification systems that those applications got delivered and are running in the way that they expect. And now they can innovate each feature at their own speed. You have these different swim lanes for feature A to feature B. I don't have to wait for this waterfall effect to go ahead and utilize a new feature that I want or to fix a security issue I've seen prior. And they've introduced a concept called CI/CD, continuous integration, continuous deployment. It reduces risk. It allows you to go ahead and stage a particular feature, understand the problems they may have to it. Developers may get code out there faster, and they can go ahead and see how it gets deployed and run in their applications in real time. Okay, so how did they do that? How did the compute guys do it? I really want to know. So let's go through a little bit of a journey here to see, kind of the major stages and fundamental items that have changed on the compute world compared a little bit to what we've seen in networking. So let's start out with Linux. All right, so Linux is the most successful open source monolithic code base that has ever existed. It has been a boon of innovation for the compute world and has allowed them to go ahead and do all sorts of fun stuff and interesting applications that we never could have done before in the old world. So what did we do on the networking side? We kind of have a similar thing. So if you go back, we had circuit switching versus packet switching. Circuit switching was around for a very long time, but it was found that packet switching was more efficient, worked better at scale, made more use of your links, and we didn't have to go with the circuit switch methodology anymore. So what was the next big change in compute? Virtualization. The ability to virtualize your particular application so now you can get more resources and better utilize what's sitting on that particular server. So you get better efficiency from the amount of RAM, amount of storage, and CPU that's on that particular device. So 15 years after Linux really starts getting traction, network finally adopts Linux. So we're 15 years later after they started, we started going, you know what, that Linux thing, that's a good idea. Maybe we should try using that on our stuff. So what do we end up where we're today? So containers. Containers are what allow us to drive a microservices containerized architecture to go ahead and drive the resiliency and the flexibility we need in our applications. And so where are we in network? NFV, Network Function Virtualization. So 15 years after you have virtualization really taking up steam, network goes, you know what, that's a good idea. We should do the same thing there. We can go and virtualize some of our functions. We can put it on a server. We can move them around. Yeah, sure, they're a little bloated. They might not work as well in certain cases, but this is the right direction we should go. So in reality, we're 15 years behind in network architecture than we are on the server side. All right, so what can we do? What's an option we can have to go ahead and solve these problems? So I think we can go ahead and start applying these cloud-native principles to the network operating system. We can utilize containerized microservices to go ahead and split up our particular protocols and functions and infrastructure on a network device, whether that be on an embedded equipment, on the cloud, or a virtualized environment. We can then take that architecture and do things not where we do patches with hotfixes. We're not putting a Band-Aid on this fix. We're doing immutable updates. We take the container and we swap it with a new container and a new version that has the fixes we need for it. It won't be off mainline, and it's a new version of code. We don't have to worry about having this off mainline patch that we're not trying to solve for a particular item. And it gives me the flexibility to run the features I need on my device and what I don't need on my device. So it allows us feature independence. So we got our little guys right there swimming in their different swim lanes. So you can go ahead and see that one at the top in the lead, that might be a BGP feature that we want to go ahead and deploy. The one at the bottom may be something we don't care that as much. Maybe it's something with spanning tree, OSPF, LDP, or maybe even just an infrastructure change that allows us to do different type of tagging on our equipment and our packets. And finally, we can do true CI/CD to drive the changes and the updates we do on the network. Sure, today we can go ahead and do a CI/CD for config, but that's not good enough. Config-driven networking is going to eventually fall down and break and not be able to drive us forward. We should be able to take a container with a protocol sitting with it, with the config or state that we want to go ahead and declare on those particular function we want to go and deploy, test it in a virtual environment, test it in the cloud, or test it on our hardware infrastructure sitting in our on-prem equipment. And it should be no difference. It's the same code. That portability doesn't exist in networking. We can't take one feature and push it across these different items and test it in a cycle that ensures that we're going to deploy something that will work. So in my opinion, a cloud-native network operating system would modernize our industry. We would have state-driven operations. That means declarative state drives network automation. We don't have to go through these complicated abstractions to go ahead and say, hey, we have a config, and then we declare state. That state gets converted into a config. That config gets converted back into a state, and we got to make some translation between the two. No, we should natively be able to declare the state we want of the network, and then verify that state is working as we expect in the NOS itself. And that brings us to a common operating model for between the NetOps folks and the DevOps folks. Now they can be on the same page on how they deploy their equipment. They can go, oh, I understand how you're doing it because you follow the same pattern, the same mechanisms that I do, and I don't have to worry about waiting on the network to go ahead and get something done or slow down my deployment of application. Containerized microservices. We've all seen the benefits of being able to go ahead and have a portability of a container, to be able to update it, be able to do security, immutable update on that particular item to ensure we get the best feature and the best function and the most up-to-date code within our network. I mean, how many people here have code running on their network switches that is more than 3 years old? Yeah, quite a few, I'd imagine, because it is so hard and difficult to update a switch without causing impact, without getting a downtime scheduled for it, and to make sure we have that coordination between what the NetOps teams are trying to do and what the DevOps application folks need to drive. And if we can do a CSED functionality where we can go ahead and test that portability between the config and the actual code that's running on there, actual function, it will ensure that we can go ahead and deploy our applications quickly, efficiently, and fast. Makes the operating of the network simpler. The same with the feature swim lanes we were just discussing, where you can go ahead and have a feature innovate at its own need, at its own speed, that is required by that particular consumer of that particular feature. And finally, and I think this is actually very important, the protocols that we use today don't need to be changed. The protocols work fine for the convergence we have. It's been proven for years. I haven't seen too many people sit there and go, you know, I wish I had a better OSPF or a better BGP. In reality, what they want is a better way to manage those items. So we don't have to go ahead and retrain ourselves on mechanisms to go ahead and find a better way to do speed and convergence for a particular protocol. We just need to find a better way to manage and to containerize our microservices for our devices to ensure we can drive a better solution forward and really move the networking industry to be on par with where our compute folks are. Cool. All right. Thanks, everyone. That's all I have to say on that topic.
Questions? I've got this down now.
Cool. Good catch.
So,
Sure.
have you met a man named Dan Cohn?
I have.
Dan Cohn, for those of us in the audience who don't know, is executive director of the Cloud Native Computing Foundation. Mm-hmm. There's an opportunity here, I would think. Certainly the man listens. He's capable of taking on new ideas. He's actively garnering them. He's asking for them. What about a Cloud Native Networking Foundation?
I agree. We just joined the Cloud Native Network Foundation on the 29th of August. So you can go ahead and look at our website and read about our blog on that. So we've already reached out with that particular group, as well as being part of Linux Foundation Networking.
Good. Congratulations.
Thank you.
Can you hear me? Oh.
I can.
All right, that sounds loud. My name is Murad Kaplan. I'm the co-founder and CEO of a company called Stateless.
Okay.
So I understand your approach of, okay, let's see what the compute did, you know, how they became like a scalable architecture, and we try to do that for networking. But one thing is, like in compute, is like the performance metrics for them is totally different than networking. Mm-hmm. You know, for example, like if you look at a firewall or a router and you try to disaggregate it,
yep.
The amount of performance that need to handle, like in terms of packets, is different than a web application.
Sure.
Like a web application can handle like 10,000, 100,000 packets, but a firewall can handle like millions, if not trillions, of packets internally. Mm-hmm. So what's your thoughts of, once you have this disaggregated architecture, how do you achieve the performance needed for networking?
So there's a couple different ways. The most obvious one to me is hardware acceleration. So we still will leverage hardware forwarded ASICs to go ahead and ensure that the data plane that we're forwarding this traffic with is still as efficient as it would be on a traditional network device. Really what it comes down to is we're not disaggregating or segmenting the data plane. We will still have, you know, a way to manage that ASIC as a separate container, but from the control plane standpoint, for the features and functionalities running there, that's where we're going to go ahead and, or where I propose that we should go and have those segmented up. So you can have BGP running its own containerized microservice, spanning tree running its own containerized microservice. You could have your RIB or your interface manager as a microservice that you could upgrade, patch, or immutably upgrade as needed. But when it comes to performance of actually forwarding the traffic, that will either be something that's accelerated on that piece of hardware or using some software mechanism that also does that sort of offloading on that. Does that answer your question? Go ahead.
Yes, it does, but at the same time, I feel like you're making bigger monolithics to a smaller monolithics. So you still like have the PGP.
Yep.
You still have like the PGP inside a container, which is similar to a PGP in a bigger container before.
Sure. So we have to take these in baby steps. I'd love to be able to take BGP, split it up into 5 different services, and have them in different containers are sitting on there. That's going to take time to go ahead and do. But in order to get to that point, we need to first enable the infrastructure and the architecture to be able to support something like that. Today, we can only take that as maybe another piece of modular code on a single monolithic binary. Cool.
Questions?
Cool. All right, thank you.
Thanks. Great. Fantastic. So this concludes FutureNet for this year. I think, if 2 lessons stand out here, it's first, stay healthy. And the second one that while service mesh is is in fashion and is the little black dress of the season, it seems like a real little black dress. It's not going to go anywhere soon. It's probably going to stay in fashion now for a while. So before we adjourn here, I want to thank a couple of people who've made this possible. So first of all, our fantastic steering committee who helped find these talks and put this together. Then of course our speakers today. Tom Gillis for sponsoring with the NSBU and providing the budget. Without that, it wouldn't happen. Bruce and Perry, my co-conspirators from VMware, for helping put together the actual speaker list and hammering out the details. Amy, Ellen, and Mike for helping with the organization, and most importantly, Kelsey Cook, who was the mastermind behind the whole organization, made sure everything worked out at the end. Thanks for coming, and I hope to see you at a future FutureNet.